should be recording this. So for Courtney and Lexi, and that's it. Identical twins will have identical banding patterns. This is all about, well, you don't need to know the mechanics of it. It's gel electrophoresis patterning. On average, do you know how much DNA you share with a non-twin sibling? About half. You share roughly half of your DNA. It can be more, it can be less. How much DNA do you share with a parent? 50%. Because each parent gives you half of your DNA. So half of your DNA comes from each parent. Can you have something in a banding pattern that one parent doesn't have? Yeah, as long as the other parent does. Can you have something show up in your banding pattern that neither parent has? No. That means the parents aren't who you think the parents are. So, it happens. Not so much with the moms. But, you know, mama's baby, daddy's maybe. Anyway, nobody watches this anyway. It's fine. So, do you see another rat that shares banding pattern? D. So, D shares this. I very often will put a line across. So, it looks like that bottom line is shared. Now, this isn't there. What about this one? I'd say that top fat one is shared. Yeah, I'd say that's shared. Then that other one's an X. There's a band in here. There's no match on that. It's unclear if that's a match. So if your options were parent or sibling, you think that's a parent or sibling? Yeah. So on average, you can have two siblings that share a lot more DNA. It's luck of the draw. But in general, they tend to share on average about 50%. And you definitely share 50% with your parents. So this could be a parent or non-identical sibling. Now what about rat B? Do you see any banding in common? I see really nothing shared. That's your unrelated individual. And the questions that are below the picture are really just to replicate what we would have done if you were doing this on air test and you were dragging stuff in. All right, let's look at the back. So another use of DNA band identification is unknown remains. So especially during the Vietnam War, we had service members who went missing and whose bodies weren't necessarily, they went missing, they weren't necessarily dead, Gesundheit. And some of them ended up making it home, but a lot of them didn't. And families want bodies to bury. Families want something to have some closure. So there was a huge project where they attempted to match any fragment that they found with living relatives. And now, the Vietnam vets are in their late 60s now, I think. They're, we're having fewer and fewer of them are going to have two living parents at this point. But in cases, and once this technology became available, any parents who still had a missing child, they got DNA samples from. So what they do is they take the DNA sample from the soldier and they look at all the possible parents. Now I'm going to tell you this is not done by human eyeballs like we're going to do it. This is done with a computer matching system, which is way better than us, but the state of Ohio thinks that you should know how to do it by hand because, it makes perfect sense. So let's just look at this, and the first thing we want to do is rule out parents who couldn't possibly be parents. I'm going to tell you in advance, I don't have an answer key for this. I don't know what the answers are. I'm as blind as you are. Okay, so right now I see a good match. I see a decent match with G and H. Obviously, we're supposed to assume that these parents are parents together, and these parents are parents together, and these parents are parents together. It kind of looks to me like D had an affair with E, but okay. I guess we're not allowed to do that. That's outside the rules. So G and H have a good match right now. A and B, neither parent has anything where the soldier has that big fat bar. Guess what? We just eliminated them. Neither of them. And if we look further down, you know, there are several instances. They have nothing here where a soldier has a big fat bar. So I'm going to just cross off A and B. And I find it easier to do these by process of elimination. I think it's easier to throw out individuals rather than try to match them first. So on G and H, we had a good match up here, but you know what I'm looking at? Look at this whole area. The soldier's got a whole ton of DNA bands there, and G and H have almost nothing there. Is that possible? Are those possible parents? Nope. Gone. Which gets us down to 2 pairs of parents. So let's look, I'm going to circle matches in green where we have them. So I'd say that's a match, that's a match. Each pair of parents has got something there. Now there's nothing, and I'm going to use my little purple line again here. Pardon? So there's nothing in there for the soldier. And that doesn't rule out anybody. But when we look down here at this nice fat band, C has a band, F has a band. When we look here, we've got a hit for each of those bands with one of the parents. Here we have hits on those bands. This one is kind of questionable, I think. Parent B had an affair with parent C. I don't know. Oh, yeah, look at that. Neither of these parents have anything in that bottom quadrant. And the soldier's got multiple bands down there. So we can eliminate E and F. So C and D are our most likely parents. And this is how they do it on like Jerry Springer and stuff. So if you get a question like this, fold up a piece of paper and make yourself a little ruler and hold it under the bands and try to level them up. It's really hard to do by eye, but this is a more complicated example. The rat one that they gave on the test one year I think is simpler. So, okay, let's look at the protein synthesis. Just realized I forgot to record any of this. So we've got our amino acid charts, square, round. We've got a sheet here. I'll put it on Classroom for anybody who's absent. And we just made a strand of RNA from DNA, remembering that C matches G, G matches C, but the apples don't fall. They fall from the trees, but they land on umbrellas in RNA. It's sketchy, but it's the best we've got. So G, G, U, what amino acid would that be? We start with G. That's our first letter. Our second letter is G. And our third letter is U, and it doesn't matter what the third letter is, because it's still going to be glycine. And what does glycine get hooked to? AUC, AUC. Isoleucine. No way I'm going to fit that in there. ISO-L. Does this feel like you can vaguely remember this? You did this plenty. So let's just do a quick overview review. So we've got our little cell nucleus. It's got little nuclear pores on it. And out of the little cell nucleus, so we've got DNA in there. But it can't come out because it's too big and it's too awkward. So a copy gets made. Remember what that copy is? One-sided RNA. RNA travels to the ribosome, gets fed through. Other little sections come over bearing gifts. By gifts, I mean amino acids. Those amino acids all get hooked together. And they form a what? What's a chain of amino acids? Protein. Yeah. And all the proteins that we've talked about, the channel proteins in your cells, the sodium-potassium pumps, which are made of protein, the proteins that form your muscles, the proteins that form anything, those are all manufactured the same way. They're manufactured in a cell, DNA to RNA, it's transcribed, then it's translated into a protein made at the ribosome, folded up in the endoplasmic reticulum, and then packaged for export by the Golgis. What other questions do you have? Relax, get a good night's sleep. You're more than your test score.